Today we're going to look at two things. First, we're going to talk about translating. So we're translating words into math. So taking words like we have in 1 through 6 and turning them into some numbers, into some expressions. And then we're going to get into making rules or using rules to represent some different functions that we're going to give you. So we have a bunch of examples that we're going to go over today. So we're just going to start from the top. So this first section up here on the top is talking about translating words into math. Zoom in a little bit here. So number 1, it gives us 12 divided by 4 in words, and it wants us to make an expression. 12 divided by 4. So we know we're going to have 12. We know we're going to have 4. And it says 12 divided by 4, so we're just going to have our division sign. These first 6, shouldn't be too complicated. We're just taking the words and making them into an expression. 6 more than a number. So our keyword here is more. 6 more than a number. So we have a number, and we want 6 more than that number. So we're going to add 6 to it. 6 more means add. Number 3, we have some number times 2 plus 3. So there's really 2 parts to this problem right here. We have some number times 2. So let's look at that first. Some number times 2. We don't know what the number is, so we're just going to call that n, and we're timesing or multiplying that number by 2. So this 2n is the same thing as saying some number times 2, and the second part of it is plus 3. So number 3, a number times 2 plus 3, we can translate that to 2n plus 3. Number 4, a number divided by 2 plus 4. So we have 2 parts here again. We have this number divided by 2, and then we have plus 4. A number, we don't know the number, so we're going to have a variable. Let's just call it x. And this number is divided by 2. And then our second part of it, plus 4. So like I said, those were pretty straightforward, just taking the words, seeing what they say, breaking it down into the parts, and making some expressions. 5 and 6 are a little bit more complicated. We have a little bit more of a story, sort of. So number 5 reads, a small company has $1,000 to distribute to its employees as a bonus. If the company has 10 employees, how much money will each employee get? So we need to figure out what exactly this problem is saying. We need to translate some expression or some problem from the words it's saying. So we know we have $1,000. That's how much the company has. And it wants to distribute it to 10 employees. So we need to figure out what operation we're going to use to do either 1,000 plus 10, 1,000 minus 10, 1,000 divided by 10. It wouldn't really make sense to do 1,000 plus 10 or 1,000 minus 10. So really we're looking at is, are we going to do 1,000 divided by 10 or 1,000 times 10? Well, the company only has $1,000 to disperse to 10 people. So if we multiplied this by 10, we would get 10,000, which doesn't make any sense because we only have $1,000. So we're going to have to divide that by 10. So each employee should get $100 as their bonus. Number 6, Jenny earns $30 a day working part-time at a supermarket. So we need to translate what this is saying into some math, into a problem. So our variable here is days. The amount of money she makes depends, her paycheck at the end of 2 weeks or a month or however often she gets paid it's going to depend on how many days she works, because it seems like her salary in this problem is fixed at $30 a day. So we'll say D equals days. We know she makes $30 a day. So her paycheck, let's say she works 5 days. If she earns $30 a day, her paycheck's going to be $150. So we're multiplying 30 times that variable 30D. So that's this problem translated into an expression that we could use to figure out how much money she would make if we knew how many days she worked. So that's top part was just kind of a little warm up into word problems. The real heart of the stuff, or the real next topic in our functions unit, is coming up with these rules to represent functions. Some of these can be, pretty tough, especially at first, as we're getting the hang of translating what it says in words, putting it into math. So it looks like we have about 6 examples that we're going to go through. Example 1 says Tim's salary as a lifeguard depends on the number of hours he works. If he's paid $9 an hour, what is salary for 3 hours, 12 hours, and 22 hours? So I've kind of broken it down for you. I have a section where you basically write down, in your own words, what is this problem saying? Then we can figure out, like we did up top, figure out what it's saying from the words to make an equation. And then I'm going to show you how we're going to use this table to plug in 3 hours, 12 hours, and 22 hours to figure out his salary or his check after working each of those amounts of hours. So in other words, this problem is saying Tim is paid $9 an hour. So I want you to write down Tim is paid $9 an hour. I mean, him working as a lifeguard, that's kind of irrelevant. Basically what we're saying, the important part of this problem is Tim is paid $9 an hour. Or, another way to say Tim is paid $9 an hour, what we're going to use to figure out our equation is he's getting paid 9 times the number of hours. Or we need to translate 9 times the number of hours to get our equation, because he's getting paid $9 an hour. So we're going to have our $9, and however many hours he works, we're going to multiply those two together to get his salary. So for translating this into an equation, we could just say our equation would be S equals 9H. So S, our salary, is going to equal 9H. So 9 times the number of H hours that he works. So in our little function table down here, we're going to plug in 3 hours, 12 hours, and 22 hours into this equation that we made, and it will give us an output, or his salary, which is ultimately what we're trying to figure out. So our input here, like we talked about last class, our input is our independent variable. It's the hours that Tim's working. Tim controls, or he controls to an extent, the hours that he works. And then we're going to plug in this amount of hours into our rule. So we're inputting the hours into the rule, which we just made right here, 9H. And the output we're getting, the result, is our salary. So this table is pretty handy because it breaks down the input, what we're plugging it into, and then what we're going to get as our output. So the problem wants to know his salary for 3 hours, 12 hours, and 22 hours. So let's input 3 hours. And we're going to plug that into this rule. We know H from this problem up here. H stands for the amount of hours. So if we input 3 hours, we're going to plug that right in for H. So if you plug 3 into the rule, we're just going to do 9 times 3. Now if you remember back to substitution, whenever we're plugging a number like this in for a variable, we're going to use our parentheses. And that just, signifies multiplication. So 9 times 3 is 27. So if he's working 3 hours, getting paid $9 an hour, his salary is going to be $27. Next one is 12 hours. We're going to do the same exact thing. If he works 12 hours, we're going to plug that in for H into our rule. 9 times 12 is $108. And finally, Tim's working 22 hours. We're going to plug 22 in for H into our rule. So 9 times 22 is 198. So I really like this table, just so you can see how you plug the input into the rule, and that rule gives us a salary. So this is pretty cool. This is why functions, like I mentioned on the first day, there's a lot of real life examples. So believe it or not, you're using functions a lot more than you think just to figure out, things like salary. So if you flip over, turn over the page, we have a second example for you. So example 2 says, the distance that Missy rides her bike depends on the number of minutes that she spends riding her bike. If she rides her bike at a constant rate of 0.15 miles per minute, what distance does Missy ride her bike in 15 minutes, 30 minutes, and 1 hour? So if we translate all the important stuff from this problem into our words here, the important part is that she's riding her bike at a constant rate of 0.15 miles per minute. And that should be more specific. That's Missy rides her bike at 0.15 miles per minute. So really what we're trying to find out in this problem, we're trying to figure out the distances Missy rides if she rides for 15 minutes, 30 minutes, and 1 hour. So if we convert this to an equation, what we're looking for is the distance. So we'll just call distance, we'll use the variable d. And if she rides at a constant rate of 0.15 miles per minute, we know we're going to have our 0.15 in there, and we're multiplying, or the thing that we're going to plug in are our minutes. That's what we're looking for to figure out what distance she rides. So d equals 0.15 m. So d stands for distance, and m stands for our minutes. Our minutes is what we're going to plug into in our table down here. Let me zoom in on the table here. So just like in the last problem, we have our input. So our input is going to be our minutes. That's what we're going to plug into our input. In our rule, we're going to plug it into 0.15 m. That's what we translated from the problem. And our output is going to be that distance that we're looking for up here. So the first question they asked for is, what distance does Missy ride in 15 minutes? So we're going to plug in 15. So 15 we're going to plug in for m. So 0.15 times 15. 0.15 times 15 is going to be 2.25 miles. The second one, we're looking for 30 minutes. So So we're going to plug in, or we're going to input 30 into our rule. So 0.15 times 30 is going to be 4.5. Finally, 60. So 1 hour, that's what it asks for. We're not going to plug 1 in for minutes because this is hours. We're plugging in minutes. That's what we figured out in our equation. M stands for minutes. So 1 hour is really 60 minutes. So we're going to plug that in. 0.15 times 60 is going to be 9 miles. So those are two pretty good real-life examples. Taking a problem, writing into our own words, kind of pulling out what's the important part, and then translating that important information into an equation, and then using our function table to put the input into the rule and then figuring out what our output is. If you move down to example 3, the question asks, is the cost a function of the number of items? Explain. So it's really saying, is the cost a function of the number of items? Is this a function? You should be able to see pretty quickly that this is not a function. And it's not a function because of right here. No. So no. This is not a function because the x value of 4 is repeated. So the second question says, can we write a rule for this table? Well, no. We can't write a rule for this table because this is not a function. Our rule wouldn't work because at 4 we could have an output of $6, but that doesn't make sense. We couldn't come up with an equation where we would plug in 4 and also get $15. So if you look at the table or whatever information it gives you and you notice that it's not a function, then just say it's not a function. We can't write a rule. So I want you to write, can't write a rule since it's not a function. So like I said, if you notice it's not a function, the problem gives you a table like this. You see a repeated x value, just say can't write a function or a rule since it's not a function and move on. So that concludes the first page. Let me get my second page here. When you walked in, you should have picked up 2 pages. If not, make sure to go to the table and get the second page. So we have example 4 at the top. Is the price a function of the number of donuts? Explain. So is this a function? Is the price a function of the number of donuts? So it's taking our 2 variables and asking, is this a function? Well, you should say to yourself, this is a function. So yes, it's a function because there are no repeated x values. Excuse me. So the second question says, can we make a rule for this table? So yes, we can make a rule for this table because it is a function. So the way I suggest taking a table and making a rule is we're going to look at the relationship between the input and the output. We're going to say, what is going on to get us from our input to our output? on each number on our input. So if we start at the input, so the number of donuts, 1, and the cost of one donut, $1.25, we need to figure out what they're doing to get from 1 to 125. So they could be adding 25 cents. They could be multiplying by 1.25. And that's really the only two things I could think of off the top of my head that's going on. So we're either adding 25 cents to get from this input to our output, or we're multiplying our input times 1.25 to get to our output. So let's look at number 2. So we said they're either adding 25 cents or multiplying by 1.25. So if we look at 2, if we were adding 25 cents, our output should be $2.25. However, our output is $2.50. So we said our second option was they might be multiplying by 1.25 to get from the input to the output. 2 times 1.25 is in fact $2.50. 3 times 1.25 is $3.75. 4 times 1.25 is $5. So that's consistent across the rest of the table. So the rule for this table, so what we're taking and inputting into our rule to get our output, that equation is y equals 1.25x. So our output, we know our output values are y, and we know our input values are x, so it's taking our input, our x, and multiplying it by 1.25 to get this output, or this y. So you could figure this out for any number of donuts. You could say, I wonder how much it costs if I ordered a dozen donuts, so 12 donuts. If I was asking in the problem, how much does it cost to order 12 donuts? That's a very reasonable question that somebody would want to know. All you would do, our input number of donuts, we would put in 12. So our output would be 1.25 times 12, which is 15, or $15. So we're going to give you a couple more examples looking at these tables, because it can be fairly challenging at first, just getting the hang of, the kind of thinking that we want you to use. Example 5. Some plants need a large amount of space in order to grow. The number of seeds that can be planted in each row is related to the length of each row. Examine the table below. Is this a function? So we're looking at our input. Are all these x values different? And it's pretty obvious that yes, this is a function. There's no repeated x values. So if it's a function, we can write a rule for this table. So we're going to do the same kind of thinking we did up top in example 4. We're going to look at the input and how it relates to the output. So from our input of 16 here, the first one, our row length, we need to figure out what is the relationship between the input and the output. So what is going on between the 16 and the 4? Let's see, we could be subtracting by 12. 16 minus 12 is 4. We could be dividing by 4. 16 divided by 4 is 4. Let's look at the second number using those two examples. So we said first, we could be subtracting 12, because 16 minus 12 is 4. So if we look at 24, is 24 minus 12? That should be 12, not 6. So let's try our second one. we said we could be dividing by 4. Is 24 divided by 4 6? Yes. Is 52 divided by 4 13? Yes. Is 64 divided by 4 16? Yes. So it looks like our rule for this table is taking the input and dividing it by 4 to get the output, because every one of these inputs divided by 4 gives us the correct output. So our rule for this table would be the number of seeds, or n, that's our output, equals our row length, we could just call length L, divided by 4. So our output, that's what we're solving for, our number of seeds equals this length or input divided by 4. Our output, or number of seeds, equals, the way to figure that out is taking the length and divided by 4. Just a couple more here. Example 6. Are the following relationships a function? Explain. If possible, write the function rule. So A. We're first asking, is this a function? So our input's 2, 5, 0, 6, 4. So this is a function. So now we need to write the function rule. So just like above, we're going to look at how the input relates to the output. So if we're looking at the one right here, this 2 and this 4, how do we get from 2 to 4? We could be adding 2. 2 plus 2 is 4. We could be multiplying by 2 to get to 4. Or we could be squaring to get to 4, because 2 squared is 4. So let's take those three things, look at 5 and 25. We said we could be adding by 2. Is 5 plus 2 25? No. So we're not adding by 2. I said we could be multiplying by 2. Is 5 times 2 25? No, 5 times 2 is 10. The third one I talked about was squaring. Is 5 squared 25? Yes, 5 times 5 is 25. Is 0 squared 0? Yes. Is 6 squared 36? Yes. Is 4 squared 16? Yes. So our output, or our y, is equal to our input, which is x, squared. So everything in our input is squared to get our output, which is represented by this equation right here. B, is the following relationship a function for B? You should see pretty quickly, no, it's not a function. There are repeated 1s and repeated 2s. No, not a function. And we know it's not a function because we have 2 sets of repeated x values. And like we said, if it's not a function, then we don't have to write a rule, because the rule won't make sense, it won't work. On the back, I want you to try these 2 examples. So if we could pause the video, I want you to try these 2 examples, and then when you're done working, you can unpause the video and you can check your answers with my work. So under you try, we have number 1. Gives us our table here, and we need to figure out the rule, how it's going from the input to the output. What equation can I make to plug in every value of my input and get this output? So if we look at 2 to 16, how could we get from 2 to 16? Let's see, we could add 14, we could multiply by 8. There's a lot of different options, because you could say, oh, we're multiplying by 10 and then subtracting 4, but let's just start basic for now. So the 2 things I'm going to look at for now are we adding 14 or are we multiplying by 8? So if we go to 5, if we're adding by 14, our output should be 19, but it's not. The other thing I said was multiplying by 8. 5 multiplied by 8 is 40. If we go to the third one, 8 times 8 is 64. 10 times 8 is 80. So it looks like our rule for this table is taking the input, multiplying it by 8 to get the output. So y, our output, to find that, we're taking our input and multiplying it by 8. So 8 times our input will give us this output, or this y value. Same exact thought process for number 2. How are we getting from our input to our output? What's going on? What's my equation that I'm plugging the input into to get the output? This one is interesting because the output is smaller than the input. So the most obvious thing to me right off the bat is it looks like it's dividing by 5. Because 5 divided by 5 is 1. Another thing they could be doing is subtracting 4. But if you look to the right, 15 minus 4 should be 11, excuse me. But it gives us 3. So the other thing we said was dividing by 5. 5 divided by 5 is 1. 15 divided by 5 is 3. 25 divided by 5 is 5. And 35 divided by 5 is 7. So it looks like to get our output, or our y value, is taking our input and dividing it by 5. So our equation for that would be y equals x, so our input divided by 5. So that just about wraps up our notes on translating and writing rules for tables. Thanks for watching.